Wanted to work through a problem that involves a diffraction grating and the diffraction pattern of a diffraction grating. A diffraction grating is a device that has a large number of narrow, thin, parallel slits. And you can characterize the diffraction grating by the separation between the individual strips, or you can characterize it by the number of those slits per centimeter or per millimeter. In this particular question, we're told that we are shining visible light, 500 nanometer wavelength light, on a diffraction grating, and we observe the third order maximum of the diffraction grating pattern at an angle of 32 degrees. And based on that information, we've got to figure out a couple of things about the diffraction grating and the diffraction pattern. The first thing is, what is the number of slits per centimeter for the diffraction grating? The separation between the slits for the diffraction grating. And then the second thing is, in total, how many maxima from the central maximum through the first order maxima and so on and so forth. What is the total number of maxima we see in the diffraction pattern of the diffraction grating? So I got a little sketch of a diffraction grating over here on the left-hand side. Here's a source of light characterized by its wavelength that's being directed onto the diffraction grating. So here's the diffraction grating. It's many parallel thin slits, and we could characterize those slits by the separation between individual slits. That would be the parameter D. We could characterize it by the number of those slits per centimeter or millimeter. That's this parameter N. And then that diffraction grating, the light that's passing through the slits of that diffraction grating, produces a diffraction pattern. It's a series of minima and maxima. It's a series of bright spots of constructive interference. And I'm picturing the location, say, of a particular bright spot at an angle theta. So the first part of the problem, A, asks us to calculate the lines per centimeter of the diffraction grating. That's the number of lines, number of slits there are per centimeter of diffraction grating. We're actually going to do it by first calculating the separation between the slits of the diffraction grating, and then we'll convert that into the number of those slits, or the number of lines per centimeter. So first I'm going to write down the information that we know about the diffraction grating and the diffraction pattern. We know the light has a wavelength that's 500 nanometers. We know that the third order, I'll put a little 3 subscript here to remind us that the third order diffraction maximum is at an angle of 32 degrees. And finally, we know that this is the third order diffraction maximum. So we know that integer m that labels the diffraction maximum. And our task here, our first task, is to actually calculate the separation between lines, separation between slits. And I'm going to do that using this equation that describes the diffraction pattern of the diffraction grating. In this equation, D is the separation between the lines of the slits. Theta is the angle of the diffraction maxima, the constructive interference. M is the order, first, second, third order, etc., of the diffraction maxima. And lambda is the wavelength of the light. In our case, we want to rearrange this equation for the spacing between the lines, the spacing between the slits. That's D, and D will equal m lambda over sine theta. Everything on the right-hand side now is known to us. So we can just fill in those quantities. We've got 3, that's the order of the diffraction maxima that we're considering. We've got 5 times 10 to the minus 7 meters. That's the wavelength of the light. And then we've got a sine of 32 degrees, the angle of the maximum. And if I calculate this quantity here, already done it, I got, it's 2.8 times 10 to the minus 6 meters. I'm going to write it as 2.8 micrometers. And that's the line spacing. That's the slit spacing of our diffraction grating. Now, actually, the question asks for a related quantity, the number of lines per centimeter. I call that number of lines N. And if we want to find that, all we got to do is actually divide 1 centimeter by the distance between a pair of individual lines. So 1 centimeter is actually 10,000 micrometers. And we're going to divide that by the distance between a pair of lines, that's 2.8 micrometers. And when I divide 1,000 micrometers, a centimeter, by the distance between a pair of lines, 2.8 micrometers, I'm just going to get a number. And this number comes out to be about 3,500. It's just the number of lines, number of slits of the diffraction grating in 1 centimeter, in 10,000 microns. In part B, we're asked to figure out the total number of maxima that we see for the diffraction grating. So we've been looking right now at just one of the maxima, the m equals 3 maxima. But how many maxima are there in total? So let's see if we can figure this out. Again, I think I'll start by writing down what I know about the diffraction pattern and the diffraction grating, just to remind us. I know the wavelength of the light is 500 nanometers. I know the slit separation now, or the line spacing now. It's 2.8 micrometers. And I know the maximum angle at which I can see a diffraction grating. The light spreads out from the diffraction grating at an angle theta, and the maximum angle that you can see to is 90 degrees away from this axis. And so I'm just going to write that theta max equals 90 degrees. And so that's the information I know in this part of the problem. And what I'm interested in this part of the problem finding out is how many of these maxima I can see. So again, we're going to start from the same sort of master equation for the diffraction grating that relates the line spacing, the angle at which the diffraction occurs at, the index, the label for the maximum, and the wavelength. But in this case, I'm going to rearrange for m in terms of the wavelength of the light, the maximum angle of the diffraction pattern, and the slit separation. So if I rearrange this equation, I'm going to get d, and I'm going to get m equals d sine theta divided by lambda. And so again, at this point, I can plug in the various numbers. D, the spacing between the lines or the slits, that's 2.8 microns. the wavelength of the light, 500 nanometers or 0.5 microns. Sine theta is 1, so I've got to multiply this by 1. And if I take this ratio here, I got 5.7. And so this equation is telling me that for 90-degree diffraction, the integer m is 5.7. Now, m is an integer. It can't be 5.7. So what it's actually telling me is that before we get to 90 degrees, before we get to this value of 5.7, I've been able to see on the screen the central maximum, that's with m equals 0, the first order maximum, plus or minus 1 for m, second order maximum, plus or minus 2, third order, fourth order, fifth order maximum, that's plus or minus 3, plus or minus 4, plus or minus 5. I see all those maxima on the screen, but I'm not able to see, say, the sixth order maximum with plus or minus 6. So just to make it clear, we see the following maxima on the screen as part of the diffraction pattern. The central maxima, the primary first order maxima, secondary second order maxima, third order, fourth order, fifth order, but no more. And so if I just count these up, there's the central, that's 1. And then for the plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 5, they're all pairs around the central maximum. That's a total of 11. So we see 11 maxima. Well, that was an example of a diffraction grating. As I said, diffraction grating has or is an arrangement of narrow, closely spaced, thin slits. It's characterized by the slit or line separation, or equivalently by the number of slits, lines per centimeter. In the first part of the problem, we use kind of the master equation for the diffraction grating, d sine theta equals m lambda, to figure out the diffraction gratings spacing, or the diffraction gratings number of lines per centimeter. Second part of the problem, knowing the diffraction grating spacing or lines per centimeter, we were able to figure out the details of the diffraction pattern we were observing, how many maxima we observed. And we saw that we saw them from the central maximum out to fifth order to m equals plus or minus 5.